Got the answers for the homework last night, worksheet number 8 up on the board. Any questions with 1 to 8, 1 to 9 on worksheet number 8? 8 and 9? Any others? Carrie? 6? 6, 8, 9, going once, going twice. All right, let's take a look at number 6. 6 says calculate the electric field experienced by an alpha particle if the net force experienced is 2.0 times 10 to the negative 16 newtons, and we want to find the initial acceleration of the alpha particle. Let's worry about one thing at a time. Let's get the electric field strength first. We're talking about an alpha particle here, so the charge of the alpha particle is on our data sheet. It says on the data sheet 2e. But an E is, of course, the elementary charge. So 2 times the elementary charge would be 2 times 1.6 times 10 to the minus 19. It gives us a charge of positive 3.20 times 10 to the minus 19 coulombs. We've got the force experienced, the magnitude of the force of 2.00 times 10 to the negative 16 newtons. And we want to find the electric field experienced. Now, in the end, does this alpha particle produce the field or experience the field? It experiences the field, right? It's feeling the field. It's where the field is. If the charge is where the field is, then it's experiencing it. If the charge is somewhere other than where the field is, right, trying to find the field strength 2 meters away from the charge, then that charge isn't an experiencer, it's a producer. But here we've got the field where the charge is. It's going to be an experiencer. We want to find the value of that electric field. So let's go E is equal to F over Q using the experiencer equation. The force is 2.00 times 10 to the minus 16. And the charge is 3.20 times 10 to the minus 19 coulombs. When we divide those two numbers, we end up getting 6.25 times 10 to the 2. And of course, the units for this are newtons per coulomb. Joel, I think you asked me a question the other day about scientific notation here and whether we had to use it or not. We wouldn't have to in this question either. We could use 625 just as easily. Just kind of a habit that I put it in scientific notation. And a lot of times on the exam, we got to do that, right? All right, first part of it's done. Now we want to find the acceleration. The reason we're saying we want to find the initial acceleration is because when these charges move, when things move, then we start experiencing a different force. And if we start experiencing a different force, then we're going to experience a different acceleration. So in the initial conditions, when the force is this value, when the distance is this value, and so on and so on and so on, what is the value of the acceleration at that point, okay, before anything changes? Well, whenever we want to find acceleration in physics 30, what are we going to do? Or at least 99% of the time, what are we going to do? A is equal to F over m. Now, most times we get a question like this, we've got to find the force using some other equation and then divide it by mass. In this case, we don't. In this case, we've got the force, we just simply divide it by the mass. It's 2.0 times 10 to the minus 16 newtons. Divide that by the mass of the alpha particle, which is, again, on your data sheet. You ever have you're ever missing data that you think you need, just check your data sheet. The mass, by the way, is 6.65 times 10 to the minus 27. We do the math on that, it works out to be 3.01 times 10 to the 10 meters per second squared. We okay with that question? Yeah? All right, let's take a look at 8 and 9 it was, I think. Is that what we said? 8 and 9. 8 says, 2 charges are in a straight row. The first charge is a value of 5 times 10 to the negative 5. The second is negative 2.5 and is 4.5 centimeters to the right of the first one. So here's charge 1. Here's charge 2. The distance between them is 4.50 centimeters, which we're probably going to want to draw attention to that centimeters because we want to be in meters, right? We've got a charge here of 5.00 times 10 to the negative 5. We've got another charge of negative 2.50 times 10 to the negative 5. And we want to find the field strength midway between them, halfway in between them. Well, the first thing we do is draw this diagram, or complete the diagram at least, that we already have up on the board. The field caused by charge 1 is going to go which way? Charge 1 is a positive charge, right? It produces a field that is which way? Towards it or away from it? Sorry? Away from it, yeah. So away from charge 1 over here is to the right. We're going to call that E1, the electric field 1. By the way, don't forget to put that arrow on top of E. Could you get this question right if you didn't? Yes. In fact, lots of times you will get this question right if you drop the vector sign over the E. But what's the danger? If you drop the vector sign over the E, what's the danger at some point? Forget the direction at the end, maybe, but even bigger than that. At some point this year, if you consistently leave off that vector sign over the E, at some point this year, I can almost guarantee that each and every one of you will mix this up with energy at some point. You'll get it mixed up with energy. Right now, it's not such a big deal. But as time goes on and we start doing more and more things, at some point, you're going to start calculating kinetic energy or something like that when you're trying to find the electric field. Put the vector sign over it. Energy is a scalar. It doesn't have the vector sign. Field is a vector. It has the vector sign. That's how we keep them straight. That's how we don't get kinetic energy and electric field mixed up. Might seem silly right now that you would get them mixed up, but trust me, almost all of you will if you forget to put the vector sign over E. All right, let's take a look at the field caused by number 2. It's a negative charge, so the field is going to point which way, toward or away? It's always going to point towards the negative producer. E2 is to the right. Now we calculate both of those fields. E1 is KQ over R squared, 8.99 times 10 to the 9. 5.00 times 10 to the minus 5. What's R going to be? 2.25 centimeters, which we're going to have to convert to meters. We could say it's 2.25 times 10 to the minus 2, or we could simply move the decimal place over 0.0225, and we got to square it. Okay, we solve for that, and when we do, it works out to be 8.879 times 10 to the 8. And the units will be newtons per coulomb. Let's get the value of E2 in the same way. K times 2.5 times 10 to the negative 5 divided by 0.0225 squared again. We end up getting 4.44 times 10 to the 8 newtons per coulomb. Now what am I going to do with both of those values? We're going to add them together. Are there any things that we have to worry about being negative? They're both positive here, right? Because why are they both positive? They're both to the right. Do you see what would happen here if I had have included this negative 2.5 in my second equation? If I had to put the sign of the charge, I would have gotten a negative value for E2. What would be the temptation there? Okay, let's say I put in the sign of the charge into my equation. What would be the temptation in this? We would look at this first one and say, oh, that's positive 8.8. The second one is, oh, it's negative 4.4. We add them up. We add up a negative value to it. We end up getting the wrong answer. For us, negative means direction. The sign of the charge we don't plug into the equation because we want to avoid what I was just talking about. Okay, make all the charges positive, get positive fields, and then worry about whether they should be right or left, therefore positive or negative. Okay, we add these up. We do end up getting 1.33 times 10 to the 9 newtons per coulomb. And it's a positive value, so it means it's to the right. Good? Yep. Yep. You guys will get a mock exam at the end of the course. It won't be for marks. It'll just be a practice thing, a full 2.5-hour exam. I was just looking at it just the other day, and there was a question, not exactly like question number 8 on the test, but almost the same. It was, you got to charge 1, you got to charge 2, and then you were trying to find the field strength over here. Okay, a certain distance to the right of charge 2. It doesn't change things, right? It doesn't make it any harder. Our distances are different here. The same basic process applies. Okay, if you can do this question, you can get that question on the mock exam and probably a question on the actual diploma exam. If you can't get this, well, then you're going to struggle with that question. And you're going to struggle probably with a question that appears on the diploma exam. So it's a good chance we're going to see this. Ask questions if you don't get it, okay? Okay, number 9. 3 charges are in a row, 3 charges The first one's got, we'll call it charge 1, and it's got a value of 2.50 times 10 to the minus 2 coulombs. Then there's another one, charge 2, that's 60 millimeters to the right of charge 1, and it has a value of negative 4.00 times 10 to the minus 2 coulombs. Then we've got another one that's 5 centimeters to the right of the second charge, and its value is positive 3.00 times 10 to the minus 2 coulombs. We want to find the field strength 2 centimeters to the right of the third charge. My goodness. What a crazy looking question. We've never done one like this before. How could I possibly expect you to do this for a homework question when we've never done one with 3 charges in electric fields before? What if this had appeared on an exam for the first time? What if we weren't doing 3 charges? What if we had only done 2 charges like in question number 8, and this question appeared on the exam for the very first time? How would we deal with that? We get 2 choices that, when we see that for the first time on an exam. We can panic. I would recommend not choosing that path. Or we can look at it and say, we know exactly what to do. So it looks a little bit different than the questions we've done so far. Who cares? We know exactly what to do here. Draw the diagram. Okay, let's find the field caused by 1, 2, and 3. The field caused by number 1 here is to the right. It goes away from number 1. Caused by number 2, it's to the left. It goes towards number 2. And the field caused by number 3 goes to the right. 3 is a positive charge, so it goes away from it. Now, do I have those drawn properly to scale? No. I have no idea which is a bigger field, so I can't draw them the proper length. That doesn't matter. Okay, we're not concerned about that in this problem. We just want the directions. So that when we go to add them up, we know whether to make them positive or negative. What are we going to do here now? One thing I should do, actually, just spotted that. Circle those millimeters and centimeters because we know we're going to have to convert those. What are we going to do at this point? Give you a hint. It's easy. Let's calculate the value of E1. It's KQ1 over R squared. What's R, though? That's the only real tricky thing with this. What's the value of R? Calculating the value of E1. The 3 distances added together. Good. 60 millimeters is 0.06 meters. Plus 0.05 meters plus 0.02 meters is 0.13 meters. So our distance here is going to be 0.13 meters. When we do the math on that, it works out to be 1.3299 times 10 to the 10 newtons per coulomb. E2 is found in a pretty similar way here. It's also KQ over R squared. This time R is going to be 5 plus 2, 7 centimeters, 0.07 meters. Don't forget to square that. Again, the most common mistake that people make, right, is forgetting to square that R. Here we get 7.388 times 10 to the 10 newtons per coulomb. Again, if we had to put a negative sign in for the charge when we solve for that, we would have gotten a negative value for field. We don't want that. Okay, we want a positive value until we start adding them up. Then we'll worry about whether it should be negative or positive. E3, the distance here is the easiest one. It's simply 2 centimeters or 0.02 meters. Here we get 6.7425 times 10 to the 11 newtons per coulomb. We got a bigger value for E3 than we did either of the other 2 charges, right? Why? Why is the value of E3, the electric field caused by number 3, bigger than the other ones? It's closer, right? Now, just because it's closer doesn't mean for sure that it's going to be a bigger value. If it's a much smaller charge, then obviously that can kind of counteract the proximity, the closeness of it. But in the end, this charge is similar in magnitude to the other 2 charges, so if it's closer, it's probably going to be a bigger field. Now we've got to add these up. The net electric field is going to be E1 plus E2 plus E3. The first one is positive. The second one is negative. The third one is positive. when we add those up, we end up getting a value of positive 6.14 times 10 to the 11 newtons per coulomb. And it's a positive value, so that means it's going to be to the right. Good? We good there, guys? Unit test coming up on Monday. Sorry, not on Monday. Sorry. Unit test coming up on Wednesday, March the 27th. Wednesday, March 27th. You guys be fine if you get a question like this on Wednesday, March 27th? Good. We'll let you know for sure next week. All right, we're going to start our next topic here, and this is certainly related to what we've been doing. We're still talking about electric fields, but now we're going to specifically talk about uniform electric fields. All of our calculations thus far have been with non-uniform fields. Now we're going to deal with uniform fields. When do we have a uniform field? Well, if you remember from our diagrams that we drew here several days ago, this would be a non-uniform field. This would be a non-uniform field. We get a uniform field whenever we have two charged parallel plates. Top plate is positive, let's say, bottom plate is negative. The field that acts in between those two plates is a uniform field. It's the same everywhere between those plates. That's what we're talking about here now. Now, it's a uniform field. That doesn't mean that the equation that we learned for an experiencer no longer applies. It does. As long as you have an experiencer in between those two plates, the experiencer equation would apply. So here's my parallel plates. Here's my little charged particle. Whether it's a positive or a negative, it doesn't matter. In between those plates, that charge is experiencing a field. Doesn't matter what kind of field it is. It's an experiencer in that field. So that equation that we learned here a little while ago still applies. However, this equation, the one that we learned for a producer, does not apply anymore. It applies to the questions we've already done. We're not going to change that. But it doesn't apply to this new situation because this is a uniform field. And this applies only in a non-uniform field. Think about it. As R changes, E changes. Well, if E changes, it's not a uniform field. You've got a non-uniform field. So don't ever try to use this equation, this one right here, when we've got parallel plates or any kind of uniform field. I remember in a third-year class, third-year university class, on electromagnetism, the entire course was on this stuff. Remember, we used to get assignments once a week, these assignments, and they were brutal assignments. And as soon as I get the assignment, I would go to the library, and I would sit there and I'd work, and I'd go there for 3 or 4 nights working on this assignment every week. And I would spend hours upon hours upon hours working on this assignment. And sometimes it was like I had no idea what was going on with a particular question. It was just insane sometimes. And I don't know why I remember this particular question. I don't remember all the details about it, but I remember this one particular question where we were dealing with parallel plates. It was a lot more complicated than the type of question you'll see with parallel plates, but still the same kind of idea. And I remember working on this question, this one question, night after night after night, probably 2 or 3 hours in itself just on that one question. And I remember at one point, just at a loss, having no idea what to do next because I just couldn't get what I was looking for. I remember trying everything, including this one, which was a complete and utter waste of time. And I knew it. I knew it was at the time. I knew you couldn't use this equation when you had 2 parallel plates. I knew it was a waste of time. I was doing it anyways because I was at a loss. But now I'm smart enough to recognize that, look, even if I'm struggling with that question, which maybe I still would struggle with that same question, there's no point in trying something that you know doesn't work. If you've got a uniform field, don't try it. No matter how much of a loss you're at here, no matter how hard this question is and how much you think you have no idea what to do, don't try something that doesn't apply. Don't use this equation. Okay? Don't do what I did in my third year university and waste your time. I don't think so, no. I don't really remember, to be honest, but I don't think I did. Now, we do have one more equation that is valid for parallel plates or anytime we have a uniform field. There's the first one, of course, E is equal to F over Q. And now we've got this last one, E is equal to delta V over delta D. There's a couple of terms in here that you're not quite familiar with. Delta D, be careful with that, is not how far the charge has moved or anything like that. It is quite simply the distance between the plates. And it's going to be measured in meters. We don't care if there's a charge in between the plates. If there is, we don't care where it is. D is not the distance from the charge to one of the plates or to the other plate, or the distance that it moves. D is quite simply every time the distance from the top plate to the bottom plate, or the left plate to the right plate, regardless of where the charge is, even if there is a charge there. Delta V, this is the tough one. We're going to spend more time next week talking about this term, delta V. But we just need to kind of introduce it now so you're able to use this equation. Delta V is what we call the potential difference between the plates. And it's going to be measured in a unit called volts, capital V. The potential difference between the plates is the difference in energy per coulomb of charge. The difference in energy per coulomb of charge between the plates. I'll give you a little analogy here. We all walk down to 7-Eleven, not today because it's like minus 50 today or something like that out there. But on another day when it's a little bit warmer and not during Physics 30 class. We all walk down to 7-Eleven. We all walk in there with $10. We all buy a Slurpee that costs $1.98. We all get $8.02 change. The money that we win, that each of us, the money per person when we went in there was $10. The money per person when we come out was $8.02, assuming we paid with debit, not with cash, because we wouldn't get the 2 cents change if we paid with cash. If you pay with debit, you only pay $8.02 or $1.98 or whatever. All right, whatever, Joel. Don't be a troublemaker. We all get our $8.02 change. The money that we go in with, each of us, the money per person is $10. The money that we come out with per person is $8.02. The difference in money per person is $1.98. The energy per coulomb of charge right here is a certain value. The energy per coulomb of charge right here is another value. The difference in energy per coulomb of charge is our potential difference. Does that make sense? It's analogous to how much money we spent on the Slurpee, the difference in energy per coulomb or the difference in money per person. Again, we'll talk more about that next week. As long as you have a kind of a basic grasp as to what it is right now, you're going to be able to use this equation. That's all I'm looking for right now. The potential difference between that plate is going to be constant regardless of where that charge is. The distance between the plates is going to be constant regardless of where that charge is. So if this number and this number are the same for this set of parallel plates, that's why the electric field strength is uniform. That electric field can't change as long as this number and this number don't change. So a little table for you. Just kind of summarizes the 3 equations that we now have for electric fields. The first equation, E is equal to kq over r squared, is valid when we have a non-uniform field. It's good for when we have a producer. Not a producer that produces a uniform field, but what we typically think of as a producer, right? Non-uniform field. We can't use it when we're dealing with an experiencer and we can't use it when we're dealing with parallel plates. Whereas the second equation, let's actually go to the third one. The third equation is valid when we have a uniform field. It's not valid around a producer. It is valid when we have an experiencer, if the experiencer is in between two plates or in a uniform field, and it is valid when we have two parallel plates. The second equation, this is what I call, and this is just my term for it, I call it the universal equation, because it's the one that's always valid. Is it valid around a producer? Well, no, but we're allowed to use it in a uniform or a non-uniform field, as long as we have an experiencer. So wherever you have an experiencer, doesn't matter what kind of field it is, you're allowed to use that second equation. What I often do is, for the math people, is draw a Venn diagram. The top one is non-uniform. We're only allowed to use that in one situation, when we have a non-uniform field. The bottom one is for a uniform field. We're only allowed to use that in one situation. That's when we have a uniform field, parallel plates, or something like that. The middle one, we can use whenever we want, as long as we have an experiencer, whether it's a uniform or a non-uniform field.